mutually exclusive events. Who remembers what a mutually exclusive event is?
That can never happen.
Events that can never happen at the same time. You can never have event A be it's raining outside, event B be it's not raining outside, and have event A and B happen at the same time. That's mutually exclusive. We will review it a couple more times today. Because independent events are different. Independent events are events that affect each other. So, two events are independent if the probability of one doesn't depend on the probability of the other. So they don't affect each other. That would be independent. Events are dependent if they do affect each other's probability of happening. And we have some basic examples to help you out. So the first example of an independent event. One card is drawn from a deck of cards and then replaced. So I have a deck of cards, I pull it out, and then I put it back in and then I reshuffle. A second card is then drawn from the deck of cards. Event A would be the first card is a heart. So what's the probability of getting a heart on your first draw? It'd be 13, because it's 13 hearts. 13 out of 52, which is just 1 out of 4. So I drew out a card, I checked to see if it was a heart, I had a 1 in 4 chance, I put it back in there, and then I asked myself to draw another card, and event B is the second card is a heart. What's the probability I draw a heart on the second time? Still 1 out of 4, it's the exact same thing. These events are independent of each other because it didn't matter what happened in the first event. This had no effect on the second event, correct? It was like it was a brand new deck of cards. If I hadn't replaced the card, then what happened on the first draw would affect what happened on the second draw. So that is an example of a dependent event. So if you read the dependent example, it says one card is drawn from a deck of cards and not replaced. The fact that it's not replaced is significant. The second card is then drawn from the deck of cards. Alright, event A. The first card drawn is a heart. We have 13 out of 52. Correct? Event B. The second card is a heart. How many hearts are left for your second draw? 12 if I took a heart out the first time. What if I didn't take a heart out the first time? Then there's still 13 hearts in the deck. And you see how that would change the probability. So there would be two situations here. The first situation would be first is a heart, first is not a heart. Yeah, X through it. It's a good way to represent it. If the first card had been a heart, then I would have 12 hearts remaining, only 51 to draw. See how the probabilities now changed from when it was replaced. If the first card wasn't a heart, there would still be 13 hearts in the deck, and there would only be 51 cards left. Yeah, so that's a good question. Let's test it out. Before, when it was independent, if you change that into a decimal, it's 0.25. If you change 12 divided by 51 into a decimal, what do you get? 235. If you put 13 divided by 51 into your calculator, what do you get? Point 13 divided by 51. Point 254. 13 divided by 51. What'd you get? 0.254901. So 254 if you round it?
No, 255.
So you can see that when the card was put back in, you still had 25% chance. When the card wasn't put back in, if you had already taken a heart out, now your chances weren't very good. They got worse. If you put the heart back in, or sorry, if you hadn't drawn a heart, your chance actually got better. And it kind of makes sense. So like if you're drawing something out of a bag, right? I have a bag, there's 2 red markers and 1 blue marker. And I reach in and I pull out a red marker. Now whoever pulls out next only has 1 red marker left to pull from, right? So they have a 50% chance, where before they had 2 reds they could have pulled out compared to 1 blue. There's actually a good example of this. Anyways, you'll notice that if you have dependent events, that it changes the probability of what's actually happening. Independent events, the probability of the events isn't altered. It stays the same. Click off of that. So, all right. We're going to go through 3 examples. We have to decide if it's dependent or independent. The first question. The experiment is rolling a die and tossing a coin. Okay, so I'm rolling a dice and throwing a coin. The first event is rolling a 2. The second event is tossing a tails. Does what I rolled on that dice change the odds of me flipping a tails? No. That thing, if it was to happen first, would have been 1 out of 2 to flip a tails. If I go and I roll a 6, the odds of me flipping a tails, still 1 out of 2. Still the exact same. These would be independent events. They don't affect each other. It does not matter what I rolled. The second question. 2 cards are drawn without replacement. And you're going to start to see a lot of card questions, and they're going to talk about replacement. So without replacement, that means I drew a card, and I didn't put it back. So that card is now taken out. The first event is the card is a king. The second event is that the card is a king. Does what happened on the first draw affect what happened on the second draw? Absolutely it does. Because if I drew, and I drew out a king, now there's only 3 kings in those cards to pull out. So there's less for me to pull out. If I drew that first deck and I didn't draw a king, well now there's 1 less card that I don't want to pull out of that deck. So these would be dependent events. That is not how you spell it. Oh, it is. It's all E's. Beautiful. I thought one of them was... Three. Try that one on your own. See if you can classify as independent or dependent. Okay, so if you're looking at this, you have a spinner. You spin it, you get red. You then spin it again. The first time I spun it, what were the odds I got red? I should say probability. What's the probability I get red the first time? Yep, there's 1 red, and then there's 1, 2, 3 other colors, so it'll be 1 out of 4. That's my probability the first time I spin it. The second time I spin it, how many reds are there that I can get? Still 1. How many other colors are there total? Still 4. It doesn't make a difference. I got a red on the first time, that's just a coincidence. That event happened, it's now in the past. We're spinning all over again. It's another random selection on the spinner. They don't affect each other. These things are independent. Next question for you. They're independent. I think people understand that they're independent. Are they mutually exclusive? Mutually exclusive is there's no way you could get the same result in both things, right? They'd have no overlap. Is it possible I get the same color the first time as I get the second time? It is. So this would be independent, but not mutually exclusive. could have got the same result on both times. And that's what mutually exclusive is that you couldn't get the same thing. So even though there was two separate things happening, you could have got the same result for both of them. But they didn't affect each other, keeping them as independent. Now you can see how these can get mixed up pretty easy, probably. How these two definitions flip-flop each other.
Would it not matter like where it lands? Like that does not make the difference.
So this is another gambling lessons again, so this class should be called. Alright, conditional probability. This is what we're kind of talking about. So conditional probability is the fact that something happening changes what's going to happen next. The way that we describe conditional probability in math is with these symbols over here. If you were to read that, where it says P bracket B, and then a bar, and then A, and then a bar, or sorry, a bracket, you would read that as the probability that B happens given that A has already happened. Okay, so that's how you could read it. The probability that B happens given that A has already happened. That's what that means when you read it. We're going to do a decent amount of conditional probability. Alternatively, you could do the condition if something doesn't happen. So if you underwrite that out, you would say P and then B, and then instead of A, you'd have A with that little complement sign, right? The little apostrophe. That would mean, what's the probability that B happens given that A doesn't happen? That could also happen, right? Let's do some examples. We're going to do a couple easier ones to start. We've already actually kind of talked about it. So this says, a card is drawn from a standard deck and not replaced. Not replaced is important. A second card is then drawn. Consider the following events. The first event would be if the first card was a heart. B would be the second card is a heart. The question then is, what's the probability that event B happens given, A has already happened? So that means they've told you something about this deck of cards. They're telling you that event A happened. So you've lost one card out of the deck. There's no longer 52 cards, there's 51. And they're also telling you that you've lost a heart out of the deck. Because they said event A happened, and event A was pulling a heart. So that means in your standard deck, you have one less card, and it was a heart. Now that you know that information, you have to try to calculate the probability of event B happening. So how many hearts would be left to draw? It would be 12 hearts. Divide by how many cards were left to draw from? 51. Because you're short one card. We did this exact question already. We put that in our calculator, find the decimal for it. What was the decimal? It was 0.235. That's right. Okay. That would be the probability of that happening, given the first event did happen. Question B. Reading that aloud, the way it would read would be, what's the probability of event B happening given that A didn't happen? So now you have one less card. And that card they drew out, what do we know about it? It wasn't a heart, so it was a spade, diamond, or club. That's what you know. So we have one less card, and it was diamond, spade, or a club. I'm just going to always shade in my clubs and not my spades. Otherwise, I look the same. So now, you have to calculate the probability of B knowing that this has changed. So how many hearts are there left to draw from? There's 13 hearts. Divide by the total number of cards that were left to draw from. 50. A good review question right now. What are the odds of this happening? So the probability is 13 over 51. Quick review. What would the odds of this happening be? Close. I'm going to see what you're trying to do. You have the one that you draw and the 50 other ones. Remember that odds is number of events you want.
13 to 38.
Yeah, and the number you don't want.
Oh.
So see, you guys got it right. The first number would be 13, because there's 13 hearts that you do want. The number after the colon would be the number of cards that are left that you don't want, which would be 51 minus 13 hearts. That means there's 38 cards in the deck you didn't want. Just want to remind you what odds were. So you're going to have to be able to swap between the two. You good? Alright, let's keep rolling. We have a couple formulas. They're there. These formulas are your independent and dependent formulas. You do need to know them. They'll be on a formula sheet for you. This formula only works if you're dependent. So this is for dependent events. And the formula is A and B happening is equal to the probability of A happening times the probability of B happening. Sorry, I said probability of A happening times probability of B happening, given you knew that A happened. Sorry. Independent events, the formula of A and B happening is just the probability that A happened times the probability that B happened. Any questions with those formulas? All right. Examples. We've talked about it already once. We're going to talk about it again right now. The difference between mutually exclusive and independent. They're different things. Mutually exclusive is two events can't have the same result. Independent is two events don't affect each other. If I flip a coin twice, those things are independent of each other. It doesn't matter what the other coin did. But they're not mutually exclusive because I could get tails and tails. That's the same result. Okay, so that's the big difference, and you need to understand that and remember that. It's easy to get it mixed up once you get in a test situation. Mutually exclusive can't occur at the same time. Independent, the probability does not affect each other. Alright, this question is going to be a little mutually exclusive and independent, but we don't know the events that are happening. So this thing says P of A equals 1 over 3. That means the probability of event A is 1/3. The probability of B is 2/5. The probability of A or B is 3/5. Investigate whether these events are mutually exclusive or independent. So we're going to see if these things are mutually exclusive. How can we check to see if something's mutually exclusive if we don't know what the events are? If you don't remember, and you rewind to yesterday, we learned this formula that said if things are mutually exclusive, that means if you add the events, it should equal A or B. So if we want to test if this is mutually exclusive, then what we need to do is we need to add P of A plus P of B and see if they equal A or B. So they should equal 3 over 5 if they're mutually exclusive. When we test this out, P of A was 1 over 3, P of B was 2 over 5. We add those numbers together in your calculator. What do you get? Did anybody do it in fraction form? What's the, you don't know fraction? Math. 11 over 15? 11 over 15 does not equal 3 over 5. So these events are not mutually exclusive. So we took our formula. Our formula said if events are mutually exclusive, then A plus B should equal A or B. Turns out, not true. So these things were not mutually exclusive. Question 2 says, are they independent of each other? So to test if they're independent, you're going to look at your independent formula. Your independent formula says A and B should equal A times B. Do we know what A and B is equal to? We don't. We don't know what this thing equals. So now we got a problem because we got to figure out what A and B does equal. To do that, you're going to have to link back to your other formulas. If you look at this formula right here, you do know A or B, you do know A, you do know B, but you don't know A and B. So you could rearrange this formula to set it up for you to be successful to figure out what A and B is. If you rewind to this slide on your page, I'm going to give you that formula. I'm going to rearrange it and give it to you. And it will not be given to you on a test. Okay? So if you rearrange or if you want to flip back and write it down, that's probably a good idea so that they're together. This formula can be manipulated by adding this one to the other side and subtracting this one from both sides. So I'm going to move that to the other side, and I'm going to add that to the other side so that they balance each other out. And this thing will become P, A, and B equals P of A plus P of B minus P of A union. So that's the same formula, but you've just flipped the signs basically on the outside. So these formulas, like this one that's bolded, will be given to you. The one that I just drew for you won't be. But it's a pretty easy manipulation to just remember. I also want you to know that it won't tell you which formulas for which thing. So see how it says like this one's for mutually exclusive events? It's not going to say that. It's just going to give you the formula. So you need to know this is for mutually exclusive, not mutually exclusive, and so on and so forth. Okay, if these things are not mutually exclusive, which we know they're not, then we can figure out that P, A, and B, I always draw an A next to N, should be equal to P of A, which is 1/3, plus P of B, which is 2 over 5, and then minus. So that's P of A plus B of B minus P of A or B happening. We know we can use this formula because we know it's not mutually exclusive, which is what question 8 proved to us. If you throw that in your calculator, you should get that P of A and B happening is going to equal 2 out of 15. That's just by putting in your calculator by math fract. Now you can test to see if this is independent or not. To test to see if this is independent or not, you need to test to see if the independent formula works. The independent formula said A and B should equal P of A times P of B. So in your calculator, you're going to have to test that thing out. So P of A and B should equal P of A times P of B. This was 2 over 15. This was 1/3 times 1/2. Put that in your calculator, you're going to get 2 over 15 equals 2 over 15. So are these things independent? Yes, they are. So independent? Yes. Mutually exclusive? No. Alright. Oh, sorry. We're going to do a couple examples of conditional probability, just to remind ourselves what that's all about. Because we've taken a slide break from it now, so we should probably just remember, make sure we're doing it right. Sure, start the video. So conditional probability can be done with questions, like we saw before, with the deck of cards. Or it could be done just straight up with using probabilities given to you where you don't even know what the events are. So the first sentence says, let A and B be events. The probability of A happening is 1 and 2. The probability of B happening is 1 and 3. The probability of A and B happening is 1 over 4. Determine probability of B given A happens. If you want to figure out PBA, you have to know if these things are independent of each other or not. How do we test if things are independent or not? This formula right here will tell us if it's independent or not. So, if these are independent, then 1/2 times 1/3 should equal 1/4. It should. When you put this in your calculator, you get 1 over 6 equals 1 over 4. So are these things independent? Are these things equal? No. So they're not independent. Since they're not independent, now you know how to calculate P of B happening if A happened already. The reason why we can do that So because these are dependent, we can use our dependent formula, which has conditional probability embedded inside of it. We can also rearrange this formula, much like we have in previous formulas, to figure out PBA. If I wanted to get it by itself, I would have to divide both sides by P of A. That would move that to the other side. So PB given A happened is equal to P of A and B divided by P of A. That's another formula that you're just going to have to be able to rearrange yourself. That one won't be given to you either. So if you want to figure out what's the probability that event B happened given A happened, you need to do the two of them together divided by the one that should have happened already. So if we want to know PBA, we need to go P of A and B divided by P of A. If you put that in your calculator, so that's going to be 1/4 divided by 1/2. If you do that in your calculator, make sure you put brackets around your fractions. Okay, so you're going to go bracket 1/4 bracket divided by bracket 1/2 bracket. Just make sure you do that in your calculator so that you're separating them and you're telling your calculator this is a fraction divided by this is a fraction. If you do that, you should get 1/2 as your answer. Is that what you get? I'm going to test it. Perfect. So we had to use a bunch of formulas to rearrange things to test to see what P of B given A actually was. The formulas can get messy fast, right? So they take practice. You have a ton of practice in your books, and you also have a lot in your unit assignment that you can work with. If we want to try this one, P of A given B happened, we're going to use the same formula we just used. You're going to use P of A and B divided by P of B this time. Because B is the event that you know happened. So the event that you know happened goes on the bottom. So you're using this formula. That'll tell you what's the event of A happening given the B. Again, you get this from your independent event, your dependent event formula. Put that in your calculator, you're going to have 1/4 divided by 1/3, and that's going to equal 3/4. Now, we're going to ask ourselves how to calculate P of A or B happening. To do that, you're going to need some sort of formula, because you have no idea what these events are. The formula that includes P of A or B happening is your mutually exclusive one. So you're going to ask yourself, are these things mutually exclusive or are they not mutually exclusive? And in this case, do you know if they're mutually exclusive or not mutually exclusive? You never said in the question, did you? And the only way to test is to already know what A union B is or A union B is. So you're kind of hooped. You don't really know which way to go with it. If you're not sure, then you should do not mutually exclusive. The reason being is these formulas are actually the same thing. If you had a mutually exclusive event, A and B has a chance of 0 happening. So it's like minusing 0 if they were mutually exclusive. So if it doesn't say if something's mutually exclusive or not, you go with this formula. That's when you go with if you're not sure. Alright. We're going to use that formula. It was P of A plus P of B minus P of A and B happening. We know that we can use that other formula because we weren't sure. P of A union B equals P A plus P B plus minus P A and B. I'm setting the calculator, you got 1/2 plus 1/3 and 1/4. Put that in, I think you over 12. I've done it. This is 0.5. I don't trust my fraction math in my head. Was I good? Is 7 over 12? Your 6 plus 3 is 9. Yeah, might increase. That's the probability of A or B. Okay, we weren't sure if that was mutually exclusive or not, right? So we just chose the second formula. We didn't know it was mutually exclusive because it never said. We didn't know what the events were. We actually could tell it was mutually exclusive. Does anybody know how? Just for fun's sake. How do we know that it was mutually exclusive, even though we don't even know what the events are? It has to do with this. What is that probability telling us? It's saying the chances that A and B happen is 1 in 4. If things are mutually exclusive, can A and B both happen? No. So the chances should have been 0 if they were mutually exclusive. But because there was a chance, it means it's not mutually exclusive. That's just a good thing to know. If you don't understand that and you're like, what? It's okay if you just stick with, do the second formula if you're not sure. Because that'll work too. Yeah, when not sure, do the second formula. Alright. Last one. The probability that Stedman will pass math this semester is 0.7. And the probability that he'll pass English is 0.9, which doesn't bode well for his math students that he teaches. If these events are independent, so it gave you a hint, they're independent events, determine the probability that he will pass math and English. If you're going to pass math and English and they're independent events, that means you multiply the two together. So you would go 0.9 times 0.7. So and means multiply them together. 63. So the chances of him doing it is 0.63. Can we switch that into probability as a fraction? You have math frac, and what's it give you for this? Could you switch that into odds? What'd you do? Be 63, because that's how many things you want to have happen on the top. And how many don't you want to have happen? 37. It'd be 100 minus 63. So this is all the things you wanted, which is the top number of probability, and all the things you didn't want, which is 37. And that's 100 minus what you did want. You're going to need to be able to do conversions like that all the way through. Right, if you want math or English, you don't care which one you pass. How are you going to figure out the probability of that thing? Should have had a formula of this too. These events are mutually exclusive or not mutually exclusive? Not mutually exclusive because you can pass both or you can fail both, right? Here's your formula for A or B happening. So you need to add the two possibilities together, but then subtract if they both happen. So if you want to pass math or English, then you're doing 0.9, that's passing English, plus 0.7, that's passing math, and then subtract 0.63, because that's passing both. What is it? 97. You can try the other two on your own. They're just examples you can already do. So give them a shot at home. Remember, you have a quiz when we come back. And it's on everything in the whole unit. Okay? Your unit test will be Thursday, so that quiz is going to be pretty indicative of where you're at. So please, please, please study. Yeah.